In the last lecture, we saw the use of convolution. Convolution is a mathematical tool which is used to calculate the output of an LTI system when the impulse response and input is available. If you remember the initial lectures, I told you there are 5 important operations we are required to study in this course. The first operation was shifting operation, both amplitude shifting and time shifting. The second operation was a scaling operation, both amplitude scaling and time scaling. There was one operation known as reversal. I'm not considering reversal as a separate operation because it is a special case of scaling operation. Amplitude reversal and time reversal both are special case of amplitude scaling and time scaling. The third operation was differentiation operation. We saw how to perform the graphical differentiation. The fourth operation was integration operation, and here also we saw how to perform the graphical integration. But we did not move to our fifth operation, that is the convolution operation, because we know convolution operation is used to calculate the output of an LTI system when the impulse response and input is given. So in this course, the convolution is mainly used to calculate the output of an LTI system. So it's good to discuss convolution once we know the basics of LTI systems. Now we know the basics of LTI systems, its important parameters, what it is, and now we can easily understand the convolution operation. Convolution operation can be used for different purposes, but in our course it is mainly used to calculate the output of an LTI system. So in this presentation, we will see the definition of convolution, we will see the mathematical formula of convolution, we will see the number of steps involved in calculating the output using the convolution, and once we are done with all these things, we will solve one question which will explain all the steps involved in calculating the output using the operation known as convolution. And after this, before ending this lecture, I will show you the animation of convolution. So this lecture is very important. Initially you will find the convolution little bit confusing, but if you know the integration well, the integration I have already explained, if you know it well, you can easily understand the convolution also. So let's begin our discussion. We will start with the definition of convolution. A convolution is an integral that expresses the amount of overlap. This is very important, the amount of overlap of one function when it is shifted over another function. So you can see 5 important points in this definition. The first point is integral. The second point is amount of overlap. The third point is one function. Fourth point is shifted over, and the fifth point is another function. So there are 2 functions involved. This is the first function, this is the second function. There is integration involved. There is amount of overlap involved when the function is shifted over the another function. This definition will be clear after solving one example. Now we will see the formula of convolution. The impulse response ht of an LTI system is given, and the input of the LTI system is also given, and now we are interested in calculating the output yt. So output yt is equal to convolution of ht and xt. So this operator here is known as convolution operator. Convolution operator, and the convolution operation between these 2 signals is equal to integration minus infinity to infinity x tau multiplied to h t minus tau d tau. So this is the formula of convolution, and I will explain all the steps involved in performing the calculations using this formula. So we are having 2 signals. The first signal is xt, the second signal is ht. So we have 2 signals, xt and ht. Here we are discussing the different steps involved in calculating the output using the convolution. So in first step, we are required to replace t by a dummy variable tau. We will replace t by a dummy variable tau. We already know the reason to replace t by dummy variable tau, we are going to move our signal. We are going to shift or move our signal waveform, and for that we will vary the time t. So we don't want to confuse between the particular instant of time t and the variable time t we are having in the signals. So it's good to replace t by tau. It will eliminate all the confusions while calculations. So we will have x of tau, and here we will have h of tau. This is step number 1. Now we want one signal to get fixed. We want one signal to remain on its own position, and we want x tau to remain on its own position, because this another function here will remain on its own position, and this function here we will shift and calculate the total amount of overlap. So we are interested in moving ht, which is now h tau, and for this we will first perform the time reversal operation, or you can say the scaling operation, and this will give us h minus tau. Actually we are implementing the formula written here, because using this formula we can easily perform the convolution, and we will have our output yt. So we have x of tau, and we are trying to get ht minus tau. We have obtained h minus tau. Now it's time to perform the time shifting. We are performing the time shifting operation, and we know one important point related to multiple operations. The time scaling operation and the time shifting operation is only performed against the variable we are having. The variable is tau, so we cannot perform the time shifting against minus tau. So it is important to take the negative sign out. We are having tau, and here we will subtract t, and when you simplify this you will have h t minus tau. The same thing we are having here, but this is the exact process we need to follow. We will perform the time shifting against tau because it is our independent variable now. It is a dummy variable which is acting as an independent variable. So we are done with time shifting. We have ht minus tau, we already had x tau, and now we will multiply them. So we will have x tau multiplied to ht minus tau, and once you have the result of multiplication you need to perform the integration. So from here we will have integration minus infinity to infinity x tau multiplied to ht minus tau d tau. So we are done with all these steps. The step number 1 is to replace t by tau. We will have x tau, we will fix it, and then in step number 2 we will perform the time reversal. We will have h minus tau. In step number 3 we will perform time shifting against tau. This will give us ht minus tau. The step number 4 is to multiply x tau and ht minus tau, and the fifth step, the last step, is to perform the integration. So these are the 5 steps involved in the convolution operation, and now we will move to our example. In this example we have xt, the input of the LTI system, and we also have ht, the impulse response of the LTI system, and we are interested in calculating the output of the LTI system. So I will quickly draw the waveforms of input and the impulse response. We are performing the graphical convolution here following all the 5 steps. So let's see how the waveforms look. The pink waveform is the waveform of input xt, and the green waveform is the waveform of the impulse response ht. Both are square waveforms, but the width of the first waveform of xt is more as compared to the width of second waveform, the waveform of ht, and it is important to notice their widths because we will obtain one important conclusion after obtaining the output yt. Now we will perform our step number 1, in which we will replace t by tau in both the waveforms. So let's quickly remove t and replace it by tau. Here we will have x tau, tau, h tau, tau. So we are done with step number 1. Now in step number 2 we will perform the time reversal, that is the special case of time scaling. In the signal h tau we will keep x tau as it is, and we will perform the time scaling, which is the time reversal to be exact. So this is how the waveform of h minus tau will look. We have simply obtained the mirror image about the y-axis, and this is the waveform. Now we will move to step number 3, in which we will perform the time shifting, and we know the process of performing the time shifting. I will directly plot the waveform of h t minus tau, but first let us mention that we have performed the time scaling or time reversal to obtain this waveform, and now we will perform the next operation, that is time shifting operation. I will quickly plot the waveform after performing the time shifting. So this is the waveform of h t minus tau. Now don't confuse yourself that the signal is shifted towards the left. Why signal is not shifted towards the right? Because t can be positive or it can be negative. We will start performing the integration by moving our signal from infinity towards the right. Our signal x tau is non-zero from 0 to 2, and we will start moving our signal h t minus tau from infinity, and we will calculate all the possible values of this integration. But it is smart choice to look for the time instants at which the signal value is changing. For example, when tau is equal to 0, the signal value is changing from 0 to 1, and when tau is equal to 2, the signal value is changing from 1 to 0. So these points or time instants are very important to perform the convolution, because we don't want to perform the convolution for each and every small increment in time. I will explain this in the next steps, but for now keep one thing in your mind. After performing the time shifting, this waveform can shift towards the right also depending on the value of t, but we want to move our signal from minus infinity towards the right, so we are considering the value of t such that the signal is shifted towards the left. So this is all for step number 3. Now we will move to step number 4 and step number 5. We will perform step number 4 and step number 5 multiple times. It is repeated. 1, 2 and 3 are the steps we are required to do one time, but 4 and 5 will repeat more than one time. So let's see how we can calculate the integration by obtaining this multiplication. For this I will make another plot, which is the plot of x tau multiplied to h t minus tau. In this plot, this waveform is the waveform of x tau, and this waveform here is the waveform of h t minus tau, and we are moving h t minus tau from left. This arrow represents the movement of h t minus tau by the variation of t here. And you can see one important thing in the waveform of h t minus tau. When we shifted this waveform, the instant at which the signal value is changing from 0 to 1 becomes t minus 1, because initially it was minus 1, and when minus tau is replaced by t minus tau, we will have t minus 1. And this instant here, which is the instant at which signal value is changing from 1 to 0, is 0. That's why we have t here. 0 plus t is equal to t. And this is important because we will use it while calculating the multiplication and hence the integration. Let's say this case is case number 1, and in this particular case we are considering time t to be less than 0. Here time t is less than 0. So you can see there is no overlap between the two signals ht minus tau and x tau, and as there is no overlap, the multiplication is going to be 0. So we will have x tau into ht minus tau equal to 0, and when you integrate it from minus infinity to infinity, you will get 0. So I can write yt is equal to 0 when t is less than 0. We are integrating x tau multiplied to ht minus tau. When you multiply x tau to ht minus tau, you will get 0, because ht minus tau is equal to 1 from t minus 1 to t, but in this time interval, signal x tau is equal to 0, so the multiplication is also equal to 0, and x tau is non-zero from 0 to 2, it is equal to 1, but in this time interval, ht minus tau is equal to 0, so again the multiplication is equal to 0, and elsewhere both these signals are equal to 0, so multiplication is again equal to 0. I hope you understand what I mean to say here. So the multiplication is equal to 0 and the integration of 0 is equal to 0, and the integration here is nothing but the output of the LTI system. So yt is equal to 0 in case number 1 when t is less than 0. Now we will move to our next case, which is case number 2, and in case number 2 we will consider time t to be greater than 0 but less than 1, this one here. So time t is less than 1 but greater than 0. This means this edge of the signal will exist between 0 and 1 somewhere in this region. So let's quickly plot the waveform. So here you can see there is overlapping between x tau and ht minus tau, and as we are multiplying them, we will have some non-zero value between this interval. From minus infinity to 0, you can see the two signals are not overlapping. ht minus tau, the green waveform, ht minus tau is non-zero from t minus 1 to 0, but x tau is equal to 0. So the multiplication in this interval is equal to 0. In this interval from 0 to t, the multiplication is equal to 1 because x tau is equal to 1 and ht minus tau is also equal to 1. After this, from t to 1, you can see x tau is 1 but ht minus tau is 0, so the multiplication is again equal to 0, and from 1 to 2 again multiplication is 0, and from 2 to infinity multiplication is equal to 0. So the multiplication is non-zero only between 0 to t. So we will integrate from 0 to t. There is no need to integrate from minus infinity to infinity because you will get the same result. So we don't want to waste our time writing these stuffs which will give us the result equal to 0. We will integrate from 0 to t. X tau multiplied to ht minus tau is equal to 1. So we will have integration of 1 with respect to tau. We already know integration of 1 is equal to tau. The lower limit is 0, the upper limit is t. So finally we have t. So yt is equal to t when t is less than 1 and greater than 0. Now we will move to our next case, case number 3. In this case, we will move our signal ht minus tau further. You can see we have moved signal ht minus tau from this position to this position, and now we will move it further, and this time our time t will be greater than 1 but it is less than 2. So let's see how the waveform will look. So this is how the waveform will look, and as we have already seen the two cases, we will quickly perform the calculations. In our third case, the two signals are non-zero from t minus 1 to t. You can see the signal value is equal to non-zero, the two signals are overlapping, and the multiplication x tau ht minus tau is equal to 1. So we will perform our integration from t minus 1 to t, and the result of multiplication is 1, so we have 1 d tau, and this will give us tau. The lower limit is t minus 1, the upper limit is t. Let's simplify this. It will give us t minus t plus 1. This is equal to 1. So the output yt is equal to 1 when t is less than 2 but greater than 1. Now we will move to our fourth case. In the fourth case, we will move our signal further. We will move it further, and this time t is greater than 2 but less than 3. It is greater than 2 but it is less than 3. I will quickly plot the waveform. So this is how the waveform will look in case number 4. You can see t is greater than 2 but it is less than 3, and you can see the overlapping interval. It is from tau equal to t minus 1 to tau equal to 2. So we will integrate in this interval only. The output yt is equal to integration from t minus 1 to 2, and the integration of 1 we have to perform because the multiplication is equal to 1. If you have some other result as the multiplication, you have to integrate that result. So here we will have tau, the lower limit is t minus 1, the upper limit is 2. Let's put them, 2 minus t plus 1. So it is equal to 3 minus t. Now we will move to our fifth and last case. In the fifth case, I will plot the waveform, but here you need to notice that t is greater than 3. So you can visualize what will happen to the overlapping. When you further move the green waveform towards the right, there will be no overlapping when t is greater than 3. I will show this by the help of the waveform. So you can see there is no overlapping between the two signals x tau and ht minus tau. So the output yt is simply equal to 0. So we have the output, and now we can easily obtain the output waveform. So let's quickly define our output. I will define the output here. It is not a good place to write, but I want to write the output here only. So the output yt is equal to, we will start from our first case. In the first case, the output yt is equal to 0, so it is 0, and when it is 0, it is 0 when t is less than 0. T is less than 0. From second case, we can see the output yt is equal to t, so it is t, and it is t when t is less than 1 but greater than 0. So t is less than 1 but it is greater than 0. Let's move to our case number 3. From here we have output yt equal to 1, and it is 1 when t is less than 2 but greater than 1, less than 2 but greater than 1. Let's move to our case number 4. From case number 4 we have yt equal to 3 minus t, 3 minus t when t is less than 3 but greater than 2. And from the last case, yt is 0, and it will happen when t is greater than 3. So this is your answer. You can write this as your answer, and if you want to find out the waveform, you can easily plot it using this definition, and you will see the waveform of the output is trapezoidal because we have two rectangular pulses with unequal width. So whenever you have two rectangular pulses with unequal width, you will get the trapezoidal waveform as the output, and when you convolute the equal width rectangular pulses, you will get the output as a triangular signal. So this is one important point, because sometimes while choosing the 4 options given, you can use these small properties. So I will repeat it once more. When you have two rectangular pulses with unequal width, you will get the trapezoidal signal as the output, and when you have the two signals which are rectangular but having the same width, you will get the triangular output waveform. So for now we will quickly plot the waveform of the output we have obtained. So I will plot the waveform, and once we are done with the waveform, we will obtain the expression of the waveform in terms of ramp signals. I'm telling you we will get the expression in terms of ramp signal because we have the continuous waveform. The trapezoid is a continuous waveform. From the definition of yt, you can see when t is less than 0 we have 0, when t is from 0 to 1 we have t. So we will quickly plot this part of the waveform. When time t is less than 0, yt is also equal to 0. So we will have the waveform like this. It will reach to minus infinity having the magnitude equal to 0, and after this, when t is between 0 and 1, we have yt equal to t. So before plotting the waveform, I will first mark down all the important time instances 1, 2 and 3, and now we will plot the remaining part of the waveform. From 0 to 1, yt is equal to t, so it will increase linearly like this. And from the definition you can see when t is between 1 and 2, it is equal to 1. It is constant. So we will have the waveform like this from 1 to 2, and after this, when t is between 2 and 3, we have yt equal to 3 minus t. It is equation of straight line with a negative slope and intercept equal to 3. So this is how the waveform will look, and when t is greater than 3, again yt is equal to 0 till infinity. So this is how the waveform will look, but I am interested in finding out the expression of yt in terms of ramp signals, and for this we will use the knowledge we have obtained from the lecture mathematical representations of signal waveforms. Initially we will follow the signal flow. It is like this. So yt is equal to 0, but when t is equal to 0, you can see the upward turn, and whenever there is upward turn, we take positive sign, and after taking the upward turn, the flow of the signal will change. It will become like this. And when you take the upward turn, you need to write down the magnitude of the slope. The slope magnitude you can calculate. It is 1 divided by 1. So the magnitude is 1, and the ramp signal will be rt minus 0 because the line is passing through 0. And once we have t equal to 1, again the signal will take the turn, but this time the turn is downward, and the flow of the signal will become like this. For downward turn, we take the negative sign, and again we are required to write down the magnitude of the slope. These two angles are same, so the slope will also remain same, 1, and the ramp signal will be rt minus 1 because t is equal to 1 here. And after this, when t is equal to 2, there is downward turn again. The flow of the signal will change. It will become like this. For downward turn, again we will take negative sign, and the magnitude of the slope is equal to 1 again because 1 divided by 1 is equal to 1, and the ramp signal will be rt minus 2. And after this, when we are at t equal to 3, again there is turn, which is upward turn. So plus 1, the magnitude is 1 because these two angles are same. So the magnitude of the slope is equal to 1, and after this upward turn, the flow of the signal is like this. So we will have rt minus 3. So we are done with our analysis, and now we can simplify the obtained results. From here we have rt, from here we have minus rt minus 1, and from here we have minus rt minus 2 plus rt minus 3. So in this way you can represent the output waveform in terms of ramp signals. So this is all for this lecture. You can obtain the same result using the Laplace transform, which I will explain in the coming presentations, but from next lecture we will start the properties of convolution. Now we will see the animation of the convolution we have performed in this lecture. You can see two windows. The first window is having two signals. One signal is stationary and it is x tau. The other signal is moving and it is ht minus tau. When ht minus tau is moving towards the right, the amount of overlap is increasing, and convolution is an integral which gives us the amount of overlap between the two signals when one signal is shifting towards the other signal. And you can see that in the second window. Here you can see the convolution is initially equal to 0, and then it is increasing linearly, and after some time it becomes constant, and when the signal ht minus tau is moving further, the amount of overlap is decreasing and the convolution is also decreasing and finally becomes 0. So I hope this animation is clear to you. So if you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.